Good evening, everybody, and it's my pleasure to be here. I have a few slides that I'm going to show and to talk about the issue of watershed interaction between groundwater and surface water, which is one water, and how, or what is the role played by the industry, and what are the consequences of the existing and proposed oil and gas activities in the region. So what are some of the key issues? This map shows the Horn River Basin. So we are in the northeast corner of BC, and this is what has been called the Horn River Basin. This is the Laird and Fort Nelson River intersection. The Fort Nelson River goes around here. Fort Nelson is right here. This map shows the locations and the quantity of water being allotted to the oil and gas industry from various sources. In dark blue, we have water which comes from lakes. In yellow, we have water that comes from dugouts. In this color, we have water which comes from streams and rivers. And then we have in dark brown the water from the storage. So you can see the distribution and the size. And the size, the larger the diameter, the more water is allocated. Now I have gone to the OGC website, and as of last week, these are the quantities that are being approved for extraction on a per day basis and on an annual basis. I use the unit of Olympic swimming pool. An Olympic swimming pool is 50 meters long by 25 meters wide by 2 meters thick. So it represents 2,500 cubic meters. So over a whole year, over 2,300 Olympic swimming pools of water are approved for extraction for use by oil and gas. What is important is to look at the distribution, and this is represented by this pie chart here. The majority of the water, 55%, actually comes from dugouts. 30% is approved to be extracted from streams and rivers, and the minority actually is from lakes and storage. So what's important to realize is that dugouts play a key role in the quantity of water which is approved from extraction. And what is a dugout? You remember when you were kids and you were by the ocean or by a lake, and you would dig a hole in the ground, in the sand or in the gravel, and there would be water accumulating at the bottom of that hole. You would take a little pail and remove the water, and the more you bail, the more water comes to the bottom of the hole. This is a dugout. This is a mini dugout. Dugout work with the same principle. A dugout is like a shallow dug well. This is an illustration of a shallow dug well. We have the well, and here are my aquifer. The aquifer is at rest. The top of the aquifer is the water table. Actually, the water table will have a slight slope because groundwater in the ground always moves. Groundwater is always moved from a high energy source to a low energy source. So it's always in movement. So when you want to get water from a well, you dug your well, you put a pump in it, and you turn the switch on. When you do that, you create a drawdown in the well. The drawdown represents a difference in energy locally. You have locally water at low energy and water at high energy provided by the water table. This difference of energy creates a movement of water towards your well. So water is pulled towards your well because you create this drawdown. So the principle of a dugout is the same. When the industry is interested by having water from a dugout, they dug a hole in the ground, they accumulate water at the bottom of the hole, and then they start pumping from that hole. And the water will come from the side and from the bottom, and will keep coming, and will keep coming as long as they keep pumping. So a dugout is actually a connection to a shallow aquifer. And a shallow aquifer is, by definition, connected to a wetland, connected to a lake, connected to a river. An aquifer is part of a system because water is dynamic, water moves. Last summer, I completed a project where I needed water, and that was the land I was testing. There is a big aquifer under that land. I drilled a few wells, and I started pumping at about 300 gallons a minute. And I pumped continuously for 7 days. There is a creek right here. At day 2, I started noticing that the creek was starting to drop. After 7 days of pumping, when we stopped, the creek had dropped by ½ meter. The aquifer and the creek, they are connected. This is a view of the site where this pumping took place. So I had one well right here, one here, one here. So I can assimilate this series of wells to a dugout. If I had a dugout right here and I was pumping from it, it would be the same. This is where the river was affected. This is where I have noticed drawdown, up to ½ meter in that zone. Groundwater, surface water, they are connected. When you pump from a dugout, you may affect the river nearby. Last summer, I don't know if you remember, but it was a dry summer. It was considered a drought condition. And UGC was aware of that and said, guys, we are dealing with a drought here. We have to be reasonable. So what did they do? On August, they issued this directive in saying oil and gas operators are required to suspend all short-term water withdrawal in northern BC. The rivers are under stress. Let's stop pumping. Except withdrawal of water stored in dugouts is not suspended. So guys, you can keep using your dugout. What did I show previously? 50%, see, over 55% of waters approved from extraction is from dugout. So guess what? We keep stressing the rivers because we keep pumping from dugouts. That doesn't make sense. Now, changing subject. The OGC has developed this tool called the Northeast Water Tool. They have spent time modeling the behavior of aquifers over numerous watersheds indicated in purple in order to quantify what is available as runoff, as water at surface. So this tool allows you, if you are interested to extract water from a certain location, to go on the map, to go to that location, to click, and automatically the tool will provide a picture, a map of the area above that point from which runoff is going to be collected. And it gives you a table. This table describes per month what is available globally in the watershed. And then they consider that 85% has to be kept for the fish, the bird, or the ecosystem that rely on the water system. 15% is available. And then they give you, this is the 15% which is available. And then say, guys, there are already several pads, several industries which are using the water. They already have their Section 8 application in place. So part of that water is already allocated. The remaining is still available. How much do you want? This is what this table gives you, and this is what the tool provides. So the UGC says, we know very well, we have done our homework, we have mapped, we have modeled, we know what's available, 15% is safe, let's use that. It's a good tool, they have done a lot of homework. So what is the key assumption? The key assumption that is you won't stress a river if you take 15% of the water that you see at any time during the year. So it means that if this is a river, which is the shape of its invert, this is a river in February or in September or in March, the assumption is that 15% is for grab. So we take it, and this is what happens. So the comparison of the picture before and after you have taken 15% in that situation is not too bad. There's not a large area on the side that you lose due to this additional extraction of the water. So I'm okay with that. Now let's consider this situation. A very different shape. Let's say we are 200 meters, 300 meters upstream from the previous location. So there is a little plateau here. This is my river. Let's assume I have 15% available. I take my 15%. What's happening here? It's not underwater anymore. What about all the ecosystems that rely on a wet and immersed environment in this area? They will suffer. Is this good? I don't think it's a good situation. Very recently, last year, a report was issued. This report was issued months of work by a team made of people, fisheries biologists, Alan Chapman, who is kind of the leader for water for the UGC, people from various ministries, and they came up with recommendations. Risk associated with water extraction in rivers. They call it the Risk Assessment Framework for Winter Withdrawal in northern BC. Rule of thumb, the smaller the river, the smaller the creek, the more vulnerable it is to extraction. So based on the work they have done, for very sensitive streams, they have looked at various levels of extractions. So these are the withdrawal amounts. So as you can see, we have a medium risk if we extract less than 5%. We have high risk if we extract more than 5% for a low flow stream. For a stream which is just a little higher, more than 10 cubic meters per second for mean annual discharge, we have a low risk if we extract less than 5%. Medium risk between 5 and 10%. High risk for greater than 10%. So what about the 15%?
maybe it's too high. We need to revisit that. We need to be more cautious about what we allow to extract from rivers. What we don't know. You can go online. In Victoria, they have a database that they manage, and it's called the BC Water Resource Atlas. And you can select various layers of information. So here you have selected aquifers. So this is Northeast BC. This is the Winston Reservoir. Fort St. John is right here, Hudson's Hope. Laird River, Fort Nelson River, Fort Nelson down here. This is the Fort Nelson First Nation territory. This illustration shows where we know where aquifers are, where we have mapped aquifers, where we know the approximate lateral extent of aquifers. Here, nothing. It's not because there are no aquifers, because we don't know where they are. We don't have any information about groundwater in this part of the country. We should have information. It's critical that we know where aquifers are, how thick they are, how wide they are, to which rivers they are connected. It's important. What we should know. This is a piece of land. We know the surface in green. We can see it. There is a creek flowing the little draw here. We have a drilling pad with a well. We have a few dugouts. They get water from a shallow aquifer system. Deeper, we have a thicker, larger aquifer, more like a regional type aquifer. Both these aquifers provide water to this creek here all year long, summer, winter. This groundwater is at a constant temperature. It cools the creek in the summer. It prevents freezing of the creek in the winter. This aquifer plays a key role. This one too. We have a camp nearby. They have their drinking water well. They need drinking water. They work there. So we need to know. I'll go back to that. It's very important that in every sub-watershed, in every watershed, we understand that. We know how thick this is. Is it 3 meters thick? Is it 5 meters thick? Is it 20 meters thick? Is it providing 100 cubic meter a second to that creek, or 1 cubic meter per second? If I take 50 cubic meter per second, I am going to dry out this aquifer. I'm going to take what should end up in the creek. I need to know. Same thing here. This deep aquifer, I need to know where it is. When I'm going to drill, how am I going to affect that very thick aquifer, which provides a large quantity of water to the system? I also need to understand what's happening from 0 to 3 kilometers depth. We need to visualize where the various plays are. We know we have deep aquifer system. Here, so the scale is roughly 3 kilometers here, and we have 0, 5, 10, 15, 20 kilometers. This is a horizontal scale, so there is a slight exaggeration. And we know at depth 1.5 kilometers, we have water, we have bedrock aquifers which are saturated with water. We also have dry zones, and we have a lot of mixed zones which contain both gas and water. But as a rule of thumb, groundwater is definitely present under our feet. And we need to understand what we talked about previously. and its connection to the deeper system. This is almost a scale. This is about 200 meters. This is 3 kilometers. So now, the well pad that we have here, you have a series of wells drilled down to about 3 kilometers and then extending laterally another 3 kilometers. And we're going to frack in that zone. What is going to happen for the groundwater in between here? Is it going up to the cracks? Is it going up through other drill holes? And we're going to dispose of return water, low quality water, through disposal wells, supposedly in a very confined and controlled system. But if it's not as controlled, and if we have cracks, and if my waste starts going up where I don't expect to have it, is it going to reach these systems? Is it going to end up in my creek? We need to know. We need to monitor. We have the responsibility. We are the steward of the land. What do we know in the territory? This is the Horn River Basin, so where most of the work, most of the studies have been focused. And already in this region, we are realizing how ignorant we are. So imagine about the rest of the territory. We know very, very little. So we definitely need to do our homework. We need to understand how much water is present in the subsurface at 10 meters, 20 meters, 50 meters depth. How much water is transiting, is moving in the aquifers. How much water is discharging to the rivers. The water that we see in the rivers in September is groundwater. It hasn't rained for a long time. What you see comes from the bottom of the river, from the side of the river. It's groundwater feeding the river. So we need to be very careful. If we start extracting that groundwater 500 meters, 1 kilometer away from the river, we are modifying the whole dynamic of movement of water to the river. Thank you for your attention.